Welcome to the Explainer. Today we're diving into the physics of motion to uncover a single, hidden point that secretly governs how everything moves, from a spinning wrench to an entire galaxy. It's called the center of mass. All right, let's start with a bit of a puzzle. Imagine trying to balance an object, but the one spot you need to support isn't actually on the object. It's just empty space. Is that even possible?
And believe it or not, the answer is a resounding yes. For things like a boomerang or a donut, the center of mass, that perfect balance point, is sitting right in the empty space at their center. And figuring out why is our first step to really getting a handle on the physics of motion.
So what is this invisible point that everything seems to revolve around? Let's get a nice, clear definition.
The easiest way to think of it is as the average location of all the mass in an object. It's this one special spot that moves as if the entire weight of the object is packed into it, even if that object is tumbling and spinning all over the place.
And this really gets to the heart of why this concept is so powerful. I mean, a lot of physics is just about making complicated stuff simple. And treating all of an object's mass as if it's in one spot, that's one of the most brilliant simplifications you can make. Just look at this example. If you throw a wrench, it looks totally chaotic, right? It's spinning, it's wobbling, but its center of mass travels in a perfect, smooth, predictable arc, just like a ball would. It's incredible. We can literally ignore all the complicated spinning and just focus on that one point to predict where the wrench is going to go. Okay, so this point is super useful. But how do we find it? Well, for a whole lot of everyday objects, you can pretty much just eyeball it. Yep, if an object has a nice, uniform shape and its mass is spread out evenly, its center of mass is going to be right there at its geometric center. A lot of the time, your intuition is all you need. So for a straight rod, it's right in the middle. For a ring, it's at the geometric center. Yep, in that empty space we talked about. And for a triangle, it's where its medians cross. See? Symmetry makes finding this balance point really, really simple.
But what happens when things aren't so symmetrical? What if the mass is uneven, like on a hammer that's way heavier on one end? For that, we've got to pull out a more powerful tool.
Now, don't let the word scare you off. Integration is basically just a mathematical way to find the average. It's like summing up the position of every single tiny particle in an object to find its perfect balance point. It gives us a super precise answer no matter how weird the shape is. So, for our simple rod, the whole process is about mathematically adding up the influence of every little piece from one end all the way to the other. And the result? Well, the math proves exactly what our intuition told us. The center of mass is right at the midpoint, L divided by 2.
Okay, so what happens when we use this math on other shapes? Well, physicists have crunched the numbers for all sorts of standard objects. And this gets really useful for shapes that are, parts of a whole, like a semicircle that's been cut from a full disk. For these, the center of mass will always be on their axis of symmetry, but you need some calculation to find its exact height. Using that precise math, we get some very specific formulas. So for a semicircular, that's just the outer edge, the center of mass is at a height of 2r over pi. But if you've got a solid semicircular disk where all that mass is spread out, the balance point is actually a bit higher, up at a height of 4r over 3 pi. The real takeaway here is that how the mass is distributed, that's what really matters. And this table just wraps up those key results for us. These are basically foundational formulas in mechanics that let us figure out how common shapes move without having to break out the heavy-duty math every single time. So we can find this point using symmetry, or we can find it using math. But why? Why does this actually matter in the real world? Well, like we saw with the wrench, it lets us predict motion. But it's also the absolute key to stability. An object is stable as long as its center of mass is over its base of support. It's why a low-to-the-ground race car is so hard to flip, but a tall truck is much easier to roll over. And finally, it simplifies forces. We can just pretend gravity is pulling down on this one single point. Now, here's a really cool thought experiment. What if you have a whole system of objects, say an astronaut and a spaceship, where the only forces are internal ones between them? In that situation, something amazing happens. The individual parts might be moving all over the place, but their shared center of mass, it doesn't change its path at all.
If the astronaut pushes off the spaceship, they fly apart, but their combined balance point keeps moving at the exact same speed and direction it was before. Internal forces just can't change it. And that kind of leads us to a final, pretty mind-bending thought. This one idea scales all the way up from a tumbling wrench to a swirling galaxy. Every single system has a balance point, which kind of makes you wonder, where's the hidden balance point of the entire universe?